quantum rules that behave like code. Start with the most famous riddle in the lab, the double-slit experiment. Fire single photons one at a time toward two narrow openings. If you don't look, a wave-like interference pattern builds up on the screen, bright, dark, bright like ripples crossing. But place detectors to ask, which slit did it take? And the pattern vanishes. The photon behaves like a particle. The only difference is a yes or no query. That's not a billiard ball changing its mind. That's a system responding to a question and input by updating its state. Code runs, output changes. Entanglement turns it up. Prepare a pair of particles whose properties are linked. Pull them miles apart. Measure one and you can predict the other instantly. No signal flew faster than light. Instead, the information describing their joint state was already shared. In a holographic world, far apart in 3D can still be neighbors in the boundary's data structure. The distance that matters is informational. Entangled bits sit next to each other in the code, even when their projections look separated. This is where the universe starts to feel like a quantum computer. A classical bit is 0 or 1. A quantum bit, a qubit, can be a superposition of both until a measurement. Combine qubits and the space of possibilities explodes. Entangle them and you create structure across that space. Quantum algorithms, like those being built in labs right now, don't just try choices in sequence. They choreograph interference so wrong answers cancel and right ones add. The trick isn't speed, it's parallel possibility sculpted by rules. Now bring that lens back to physics. Quantum theory says systems evolve smoothly and reversibly according to the Schrödinger equation, until a measurement when outcomes appear with specific probabilities. Two modes of update: deterministic and unitary between observations, stochastic and decisive when you couple to a measuring apparatus. From a code perspective, these are two layers of logic: continuous evolution, then a read-write event that fixes values in a particular basis. We don't yet know the full story of how consciousness fits here, and we won't pretend. But the pattern is clear. The universe keeps options open, then commits when queried by an interaction that can amplify a microstate into a macroscopic record. The commitment matters. Every record, every irreversible trace costs energy. Landor's principle tells us erasing a bit requires a minimum energy toll. Information is physical because changing it disturbs the world. That's why measurements heat apparatus, why computation needs cooling, why there's no free lunch when you compress, copy, or delete. Thermodynamics and information theory aren't separate books, they share margins and page numbers. Black holes bring this together. Their entropy scales with surface area. Bekenstein's law and Hawking radiation return scrambled information. In AD-SCFT, the boundary quantum field theory evolves unitarily. No information is lost. The bulk gravity story is a dual description that emerges from boundary entanglement. The Ryu-Takayanagi formula even equates the entanglement entropy of a region on the boundary to the area of a minimal surface in the bulk. Translation: geometry is bookkeeping for who's entangled with whom. And error correction sits at the heart of it. In holographic toy models and related tensor network constructions, the mapping from boundary qubits to bulk degrees of freedom acts like a code. Lose part of the boundary, noise, deletion, and you can still reconstruct the interior operators from what remains. That's why the bulk feels stable in these models. It's not mystical robustness, it's redundancy engineered by the way the encoding works. Skeptics point to continuity. If everything is information, where's the grid? We address that trap. Replace coordinates with relations. Who can influence whom? Causal sets and hypergraph programs catalog causal adjacency, not meterstick distance. Lorentz symmetry can, in principle, emerge in that world because nothing privileges a universal clock tick. Time steps become update events constrained by causality, not metronome beats. Sabine Hassenfelder pointed out the pitfalls of naive lattices. The response wasn't to abandon computation, it was to deepen it, making the substrate relational so symmetries can emerge. Meanwhile, the constants look like compiler flags. The speed of light caps how fast influence can propagate. Planck's constant sets the granularity of action. The Bekenstein Bound limits storage per area. These aren't decorations. They're constraints that any valid program of physics must satisfy. Inside those constraints, complexity blooms because the rules allow feedback, copying with mutation, and networks that rewire themselves. You already live this. Close your eyes. Memory is an encoding that resists noise. Perception is inference from finite, lossy data. Your brain exploits redundancy across neurons, across time, to reconstruct a stable world from partial signals. It's quantum mechanics at the bottom and error correction all the way up. Consciousness is its own conversation, but we can say this. Minds evolved to navigate an information-limited environment by becoming efficient compressors and predictors. Now flip the viewpoint. What if we're not just passengers inside the computation but components? Every observation you make is a tiny measurement event, a local collapse that writes a bit into the shared record. In that sense, we participate in selecting realized branches from quantum possibility, not as magicians, as collaborators constrained by the same rules that govern stars and black holes. Seth Lloyd once estimated the universe's total logical operation since the Big Bang. The number is vast, but that's not the headline. The headline is that you can think of cosmic history as computation without breaking any laws. Each particle interaction, each entangling scatter, each decoherence event is a line executed in a program that compiles into galaxies, chemistry, and cells. Here's the payoff. When quantum rules behave like code, gravity stops being a mysterious curvature imposed from above. It becomes the large-scale pattern that emerges when information arranges itself to be consistent, compressed, and recoverable. Stitch entanglement tightly, and space knits closer. Thin it, and space loosens. The force that keeps your feet on the ground may be the universe's way of keeping its story straight. The hologram, reality as a storage hack. Start with the constraint that changed the map. The Bekenstein Bound says the maximum information in any region isn't set by volume, it's set by the area of its boundary. That's not a poetic idea. It's a hard limit that shows up wherever gravity gets serious. If you try to pack more bits into a region than its surface can encode, gravity answers by making a black hole. In other words, nature enforces compression. The universe saves to the surface. That's the storage hack at the heart of the holographic principle. If all the physical detail inside can be represented on the outside, then the cheapest way to store reality is to write it to the boundary. Not because the universe likes metaphors, but because that's the only way to keep information consistent without violating gravity's bookkeeping. The interior becomes a reconstruction, a view created on demand from encoded data. SCFT made this operational. In Maldacner's duality, every bulk process, falling, colliding, curving, is mirrored by boundary dynamics. You can solve a gravity problem by doing quantum field theory on the edge, and it isn't approximate. In the right setups, it's exact. That's why it's a hack and not a hand wave. Two descriptions, one physics and the boundary one has no gravity at all. Gravity emerges from entanglement and correlation patterns, not from a fundamental force law etched in stone. Here's where the Ryu Takuyanagi insight changes the picture. In SCFT, the entanglement entropy of a boundary region equals the area of a minimal surface in the bulk that hangs from that region's rim. Entropy on the edge draws an invisible soap film inside, and its area gives you the number. You can flip that around. If you know how parts of the boundary are entangled, you can infer the shape of space in the bulk, within the scope of those models. Geometry becomes a ledger of who is correlated with whom. Now add error correction, and the hack becomes robust. In holographic codes, the mapping from boundary qubits to bulk operators is redundant by design. You can lose pieces of the boundary and still recover the interior operator from the remainder. That's why the inside can survive noise. It's not that the bulk is invulnerable, it's that the map recovers it from multiple overlapping encodings. A crash-resistant file system masquerading as a universe. If space is stitched by entanglement, gravity is the tendency of that stitching to tighten where information concentrates. Put mass energy in a region, and you change the pattern of correlations on the boundary. The minimal surfaces that dip through the bulk reshape, and the geometry they define curves. That curvature is what we call gravity. It's not a bolt-on. It's an accounting response to how information is distributed. Skeptics ask, our cosmos is anti-de Sitter space. True. The most precise duality lives in negatively curved universes with neat boundaries, but the ideas have legs. Physicists have generalized pieces of the story to spacetimes closer to ours, and the methods, tensor networks, entanglement wedges, quantum extremal surfaces, keep finding new uses. Even when a precise duality isn't established, a recurring pattern appears. Area tracks entropy, and geometry tracks correlation. This is more than math pride. It changes how you think about locality. In the bulk, points sit next to each other because the boundary encodes them with heavy shared entanglement. Reduce those ties and the bulk points drift apart. In extreme cases, tearing entanglement, you can disconnect regions that still look adjacent in naive coordinates. Locality is a property of the code structure, not an axiom. You already use versions of this in technology. A photograph stored with redundancy can be reconstructed after partial loss. A video stream stays smooth because error-correcting packets fill gaps. Holography is that idea pushed to the limit. The file of a whole region of space is stored on its boundary with enough redundancy to rebuild the inside under noise and loss. When we say the world is a projection, we don't mean it's fake. We mean projection is an efficient way to keep the world consistent when memory lives at the edge. There's a deeper economy playing out. The laws we measure look like rules optimized for compression and recoverability under the Bekenstein Bound. The speed of light caps update speed across the code. Planck's constant sets the grain of action per change. The area law forces surface-based storage. Within those constraints, the holographic architecture minimizes cost. Compute on the boundary, reconstruct the interior only as needed, keep redundancy high so local errors don't cascade. Black holes, once villains, become model devices. They saturate the bound. They scramble information fast, then return it late, highly mixed, but recoverable in principle if quantum gravity is unitary, as AD-SCFT strongly suggests. They show what happens when you push storage to the limit. The screen goes black, the file is still there, and the universe insists you can't read it faster than the rules allow. So the hologram isn't a trick, it's a policy. Reality favors surfaces because surfaces can carry the load without breaking quantum mechanics or gravity. Space is the visualization that helps finite creatures like us navigate the output. And gravity is the visible side effect of the code keeping its ledger balanced at the edge. We thought solidity made the world real. Maybe what makes it real is that it's stored well. Error correction in the fabric. If geometry really tracks entanglement, then stability has to come from something smarter than luck. Codes don't just store, they protect. That's the quiet revelation inside holography. The bulk feels reliable because the boundary acts like a quantum error-correcting code designed to keep meaning intact while noise does its worst. Think of a simple story. You write a sentence on 3 separate cards and hand them to 3 friends. One card gets smudged, but 2 are clean, so the message survives. That's classical redundancy. Quantum codes go further. They spread a qubit state across many physical qubits so that no single piece reveals the whole, yet enough pieces can reconstruct it. Lose a chunk, and the logic still recovers the original. Holographic duality builds that logic into the world. The mapping from boundary degrees of freedom to bulk operators is deliberately redundant. A bulk excitation, what you'd call a particle or a local disturbance, can be reconstructed from multiple, overlapping regions on the boundary. Not one unique place, but many different entanglement wedges that each contain enough of the code to rebuild the interior operator. That's why the inside isn't fragile. It's supported by a web of overlapping encodings. Now add the Ryu, Takuyanagi picture back in. Those minimal surfaces hanging into the bulk carve out the entanglement wedge for a boundary region. If your wedge contains a bulk operator, you can, in principle, reconstruct it from that region's data alone. Two different boundary regions with different wedges can each recover the same bulk operator. That's error correction in action, multiple recoveries from independent views. This isn't armchair poetry. Toy models using tensor networks, MERA-like constructions, and HOPPY codes make the redundancy visible. You lay down a tiling that maps a few bulk degrees of freedom into many boundary legs through layers of isometries. Cut off some legs, simulate loss, noise, or measurement, and the network still decodes the bulk state from what remains. The picture looks like a geometric snowflake, but the function is pure reliability. Local damage at the edge does not instantly tear a hole in the middle. Here's the human moment. A mission control team loses a telemetry channel during re-entry. Not a problem. Crosschecks reconstruct the missing numbers from other feeds. Meanwhile, across town, an engineer's laptop crashes, but autosave rebuilds the document from fragments. Neither feels magical because we intuit how redundancy works. Physics appears stable for the same reason. Only the redundancy is woven into the entanglement that shapes space itself. Error correction also clarifies an old worry. If the inside of a black hole is encoded on the horizon, and Hawking radiation carries information away, how does the story stay consistent? In a code, information can be delocalized without being duplicated. Early radiation is nearly useless. As evaporation proceeds, subtle correlations accumulate until, past the page time, recovery becomes possible in principle. No cloning happens. The code just reassigns where the recoverable support lives, first the horizon, then increasingly the radiation. What looked like paradox is a bookkeeping mistake ignored by anyone who builds reliable systems for a living. There's another payoff. Codes explain why low-energy bulk physics looks local even though the true encoding is wildly non-local on the boundary. Locality in the interior comes from how logical operators are supported on many boundary regions in a way that preserves their commutation structure. You act on one logical degree of freedom, and others barely notice, even though the physical qubits overlap. That's how you get particles that don't instantaneously talk across the room despite being encoded by shared boundary stuff. The flip side is fragility with purpose. Not every error is harmless. Corrupt the wrong pattern, enough adjacent boundary regions, and reconstruction fails for the corresponding interior wedge. In SpaceTime language, that looks like a horizon forming or a region becoming inaccessible. The code announces without drama, you asked for more than the redundancy can bear. Geometry reflects the same message. Now connect this back to emergent gravity. If entanglement patterns tighten where information is dense, the code must continually rebalance to keep logical operators recoverable under the Bekenstein Bound. That rebalancing shows up as curvature, geodesics bending, minimal surfaces reshaping, light cones tilting. Gravity is the system's way of maintaining decodability under finite storage and finite speed update constraints. You can see the same theme in our machines. Quantum computers fight decoherence by encoding logical qubits in surface codes that tolerate local errors. Classical networks maintain consensus via parity checks, read, Solomon blocks, and distributed ledgers. All of it is about preserving global truth when local pieces misbehave. The universe runs the deluxe version, a relational code that makes space from entanglement and keeps meaning alive as noise, heat, and measurement chip away. This perspective also reframes why we don't notice microscopic reversibility. Measurement writes outcomes into macroscopic records that the code now treats as constraints. You can't just unring the bell because the correction logic has accepted the update. Entropy increases not because information disappears, but because it diffuses into degrees of freedom that would require astronomical coordination to reassemble. So when a gravitational wave crosses Earth and LIGO catches a wobble in spacetime, think of it as a code pulse. a temporary reshaping of which boundary partitions best reconstruct which interior modes. When cosmic rays hit the atmosphere, you're watching the system mix, spread, and correct. And when you remember a name after forgetting it for days, redundancy saves you again. The trace was there, encoded in overlaps, waiting for a cue to decode. Error correction isn't a metaphor glued to physics. It's the policy physics seems to follow to exist at all. The world stays legible because the code that makes it prefers recoverable stories over fragile ones, and writes them redundantly on the only medium big enough to hold them: the edge. Energy, computation, and the cost of knowing. Start with a simple claim that's easy to miss. Every time you learn something, the universe heats up. Not poetry, physics. Landor's principle says erasing one bit of information costs at least kT ln2 of energy dissipated as heat.